All right, we're continuing with the curve sketching example problems. This is going to be the 8th example problem. In this video, we're going to sketch this function here. All right, step 1, the domain. What's the domain here? Well, we know that the sine of x and cosine of x, the domain is all real numbers. Okay, so the only potential domain issue here is dividing by 0, which occurs when 1 plus cosine of x is equal to 0. Okay, so let's solve for x here. All right, inverse cosine of minus 1 is pi. However, we have to think about this in the sense that the answer here is not just pi, it's pi or 3 pi or 4 or 5 pi. Right? If you think about the unit circle, what's happening here is whenever you get here, the angle is pi. So the cosine is negative 1. When it's just 0, the cosine is 1. But it could be any multiple. It could be pi, it could be 3 pi, 5 pi. It could be negative pi, negative 3 pi, negative 5 pi. Okay, so really the answer here, the technically correct answer here is x is equal to 2n minus 1 pi, where n is any integer. Okay, so you could pick any integer you want, positive or negative integer. The result you get, if you plug that in here, you're going to be dividing by 0. Now, what I want to do is, instead of giving the domain for all real numbers and giving answers like this for for any integer, I want to sketch the curve only along a certain range, and that range is going to be one period. So I'm assuming that this is going to be periodic. I don't know what the period is though. Let's look at that right now. Let's say, okay, there's some p such that y of x plus p is equal to y of x. Okay, so with that, if we come here and we say, okay, sine of x divided by 1 plus cosine of x. Okay, well, let's do this. Let's store this as e. All right. Now, so it simplifies to, well, okay. All right. So let's see if this, since the sine of x and the cosine of x have period 2 pi, let's see what, let's plug in x plus 2 pi and see if 2 pi is the period. And yeah, there we go. So we plug in x plus 2 pi for x into the original function, and we get back the original function. So the period here is, it's periodic with p equal to 2 pi. Okay, now with that in mind, we're just going to sketch one period from minus pi to pi. In that case, the domain I'm going to say is minus pi to pi. All right, but technically the domain for, if you went to all real numbers, the domain would be any x except for when x is equal to 2n minus 1 times pi when n is any integer. Okay, now the range we're going to come to once we sketch the graph, we'll come back to the range. Now let's get the intercepts. Let's get the y-intercepts. Set x equal to 0 and solve for y. So sine of 0 over 1 plus cosine of 0. This is 1 plus 1. So 0 over 2, 0. Okay. So the origin is an intercept. And what I'm going to do is, let's go from minus 5 to 5. And then same here, 5 to minus 5. That should give us a good look at this. Okay, now the x-intercepts, set y equal to 0 and solve for x. So this is where the sine of x equals 0. So inverse sine of 0. Okay, now this is like, 0, 2 pi, 4 pi, etc. But we're only going, well, okay, no, this is x is equal to stay within the domain that we're working with here. It would be 0, 2 pi, negative 2 pi, so just 0. That's the only intercepts. For we're drawing one period, we're going to draw one period of this function between minus pi and pi. We're going to go from minus pi to pi. That's going to be, so that's a period of 2 pi. We're going to draw one period, and that one period, the intercept is only at 0, x and y intercept. All right. So now the other forms of symmetry, let's check for an even function. Okay. All right. This is equal to, so we would do like that, minus tangent x divided by 2. So it's, what this is saying is just minus that. And this is not equal to the original function. Okay. What about an odd function? Minus y of x is equal to minus and this is equal to y of minus x. So this is an odd function. Okay? So for every point on the graph, x, y, any point on the graph, if you multiply each of those by minus 1, you're gonna also be on the graph. That's what the meaning of odd function is. It's symmetric about the origin. All right. Now let's do endpoint behavior. We take the limit as x approaches each of the endpoints. So let's go start with the limit as x approaches minus pi. This will be from the right of, okay, so this is the limit of our function with respect to x approaching pi from the positive direction, negative infinity. Okay. Now, what is the limit as x? Or wait, no. That's not right. This should be minus pi. Okay, so it is minus infinity. Okay. Now, what is the limit as x approaches pi from the left? It's positive infinity. Okay, so as x approaches pi from the left, This is positive infinity. Okay, so that's the endpoint behavior. Now, one thing to note here is that these are kind of like vertical asymptotes. And well, they are technically vertical asymptotes, especially if you drew out the entire function. But like what I mean by when I say kind of, it's like the log of x, the graph of the log of x is something like this. So if you take the limit as x approaches 0 from the right of log of x, you get negative infinity. But x is equal to 0 and the log of x is an endpoint. It's not really a vertical asymptote. Like it's not in the middle of the domain, you know. It is a vertical asymptote, but it's different than, you know, it's different than how we typically analyze vertical asymptotes in curve sketching. So yes, these are vertical asymptotes, okay, but it's a little different than how we analyze curve sketching because they're not in the middle of our domain here. It's more of the endpoint behavior, but they are vertical asymptotes. So and why are they vertical asymptotes? Because we're taking the limit as x approaches a single x value. X is equal to a constant, and it's going to infinity. X is equal to a constant is a vertical line. Okay, so let's draw the vertical asymptotes. So -1, -2, -3. Okay, this would be -3.5, -3.25. So right around there. Okay. Okay, 1, 2, 3. All right. There's the vertical asymptotes. And we're not drawing what's going on we're not drawing anything in these regions here. And why not? Because it's periodic. So we could just, if we wanted to draw it, we wouldn't have to do any of this analysis because it's periodic. It's just going to repeat. The pattern that we're going to draw inside here is just going to repeat. Okay. Next, let's get we know what the behavior, let's draw this behavior as well. So as x approaches -pi from the right, goes to negative infinity. So we'll be doing like that. And then as x approaches pi from the left, goes to positive infinity. So it'll be doing like that. In fact, I'm just going to leave that off for now. Okay. Next, let's get critical points outside of the endpoints. Okay, so first let's go to critical points with respect to the first derivative. All right. So derivative with respect to x of e. Okay, so there's nowhere where this equals 0. Is there anywhere where this doesn't exist? So what we can do is let's solve for when this is equal to 0 for x. Okay, so at -pi and pi. But that's at the endpoint. So there's nowhere where this doesn't exist within the endpoints. So none. Okay, what about the second derivative? All right. Okay. Where does solve for where this equals 0 for x? X is equal to 0, and then x is equal to -2pi and +2pi. So just x is equal to 0. All right. Now let's solve for where this equals 0. Okay, so that would be minus pi and pi, so that's it. So just at 0, 0. We have a critical point with respect to the second derivative. Now, from here, we could take, if this was a critical point where the second derivative didn't exist, then we would take the limit as x approaches this point and see if there's that's potentially a vertical asymptote, or just see what's going on there. If you have critical points with respect to the first or second derivative that don't exist, then you want to take the limit as x approaches that point of the derivative and of the function and of the first derivative and even of the second derivative, just to see how the function is behaving as it approaches that point. But if it's just a point of just where the first or second derivative is equal to 0, then you don't really need to do that, because you already know how it's behaving, because the first and second derivative are equal to 0. It's changing concavity, or it's changing, increasing to decreasing, or decreasing to increasing, things like that. Okay, so now let's do the intervals of the increasing, decreasing intervals. So there's no points where there's no critical points with respect to the first derivative. Okay, so that means that the curve in between minus pi and pi is going to be either always increasing or always decreasing. It's never going to change. So what we need to do is we need to take the derivative and evaluate it with x is, say, equal to anything in that within minus pi to pi. So it's positive. So it's going to be increasing everywhere. Okay, now there's only one critical point with respect to the second derivative. So there's two regions here. And at x is equal to 0, you could potentially switch concavity. All right, so derivative d squared dx. Okay, so we just need to check with x equal to, let's do minus 2. That's okay. Let's just make sure that this is, yeah. So concave down. And now do we switch to concave up? Yes. Okay, so this is an inflection point. We know the curve is going to be continuous at this point. So since it's continuous and there's a switch from concave down to concave up at that point, then that's an inflection point. There's no local maxes or mins. There's no point where the first derivative test shows us that there's a local max or min. But even outside of the first derivative test, which would be like a discontinuity, potentially. At a discontinuity, you can have a local max or min that doesn't apply, that you can't use the first derivative test to see if it's a local max or min. But that's not the case here. There's no discontinuities. So there's no local maxes or mins. Okay, so let's draw the curve. All right, so we can do that behavior like that. Okay. So that's the asymptote behavior. Okay, now when we come, the only special point here is at the origin. The slope does not become 0. Only thing that happens is the concavity changes. I don't want to make the slope 0. It's not 0. Like that. Okay, so we have an inflection point here. It changes from concave down to concave up. Is that what we see? Concave down to concave up. But we're increasing the entire time. That's what we see. The limit as x approaches the endpoint minus pi from the right is negative infinity. The limit as x approaches positive pi from the left is positive infinity. Okay, it's an odd function. Yeah. For each point here, you flip about the x, and then you flip about the y, and you're back at the curve. I didn't draw it technically accurately, but that's the idea. Like this point should be, you flip here, and then you flip. So I didn't draw it technically accurately. Like this, if this is drawn accurately, then this point here, 1, 2 should be, oh, that's all right. It should be about right here. That's pretty good. Okay, but so it's odd function and it's periodic. So what does it mean that it's periodic? That means that you just come to the next period and you draw the exact same curve. It would be like that, right? This would be, it's periodic. It just repeats, same thing over and over again. All right, there you go. That's the curve. Oh, and then, yeah, the range. Now that we can see the graph, what is the range? It's all real numbers. It goes from negative infinity to infinity.